Start recording. And make sure my chat's up. All right, cool. So here's what I want to think about, right? The example problem we're going to do is this. A roller coaster car of mass 600 kilograms goes around a loop of radius 8 meters with a constant speed of 9 meters per second. Find the normal force of the track on the coaster at the bottom and the top of the loop. Right? So let's start here. So I'm going to start by drawing a picture of what we've got. What we're going to be doing is we're going to be combining circular motion with what we were doing last unit with free body diagrams and whatnot. So let me start with, here's my loop. And part A says, I want to find what is the normal force on the roller coaster car here at the bottom of the track. So I'm going to draw the car here at the bottom. And we're going to draw a free body diagram, and I'm going to just draw that diagram right on top of my picture, just to keep everything together here. So let's think about the forces acting on this. So what do you think? What forces do I have here? Feel free to put a force in the chat that you think we would have. I'll say that this is a frictionless surface too, just to make it easier. Anybody got an idea of a force we might have? Normal force, yes. And gravity, yep. Now, the interesting thing is we're used to these being the same, although we've already come across some cases where they're not. In this case, though, we want to remember the point is to make this roller coaster go in a circle, right? In order to go in a circle, you have to have a centripetal force. And centripetal force is a force that points to the center, right? So what we need is we actually need gravity to be less than normal because we need the net force to point to the center. So this is the free body diagram we have here. Right? It's a roller coaster, so we're going to say that there's no forward force. And again, I've said we're going to assume it's a frictionless surface. So that's my free body diagram. But I need more normal force than gravity in order to make this thing go in a loop. Okay. So then how do we solve this? Well, let's go ahead and do our knowns and unknowns real quick. So we know got a mass of 600 kilograms. We know we've got that the radius of this loop is 8 meters. And we know that we're going at 9 meters per second. And we're trying to find the normal force. Here's what we're going to do. We're going to actually start this very similar to how we started things in last chapter, right? remember we started with this equation. The only thing I'm going to change about that is we're going to specifically indicate that we're talking about centripetal forces here and centripetal accelerations. And if you recall from notes from last time, we know what the centripetal acceleration is. It's v squared over r. So this side becomes mv squared over r. And if we expand this side, this side should be equal to normal minus the force of gravity. Or normal minus mg. All right, now it's just a plug and chug problem. Oops. I'm getting something like 11,955 newtons. Any questions here? All right, so but I want to be clear, right? The centripetal force is being provided by a combination of normal and gravity, right? Now this becomes really interesting when we think about what's happening then at the top, right? So part A of this problem was find the normal force at the bottom. Let's see what the normal force is at the top of the loop. So let's redraw a diagram. Please stop me if I'm going too fast. So right now the card is up here and it's upside down. We want to think about what the forces are up here at the top. I'm still the same cart, right? So I have the same weight. So if I had force of gravity up here, my force of gravity is going to have to be the same down here. So I got to draw a force of gravity pointing down again. But now this time we've got to think about which direction does the normal force point, right? And this is why I showed you the demo with the hoop a moment ago. Because the hoop was what was pushing the marble in, right, to give it a centripetal force. So in this case, which way is the normal force going to point, up or down? What do you think?
Is it down?
It is down because, again, the whole point of what a normal force does, right, is it prevents you from falling through a surface. This time the surface is above me, and so the normal force is actually going to be pointing down. And in this case, they're adding together. They're helping each other out, right? Now I say the net centripetal force is MAC, or I could say that in this case, it's going to be normal plus gravity is equal to mv squared over r. So in this case, getting something like 195 newtons. Questions? Now I want to point out something, right? If I look at these two parts next to each other, let me do it this way actually. If I look at these problems next to each other, right, there's a huge difference between 11,000 newtons and 195 newtons, right? How can we account for that? Well, remember here, gravity was fighting against the centripetal force, right? And so here the normal force had to both counteract gravity and push towards the center. But when you're up here, right? When you're up here, your gravity is helping the centripetal force. So you don't need as much normal up here as you did over there. Okay. Any questions about this? There's one follow-up question I want to ask about this. Let's say, so this time I told you it was 9 meters per second. Let's say that I wanted to know what's the minimum speed the car can have at the top of the loop and still be in contact with the track. So let's think about what that means, right? If this car is going too slow and real roller coasters kind of, there's a way that prevents them from falling off. But assume that this was just sort of a flat track, right? If this thing wasn't going fast enough, it might get up and it might fall off, right? Why would that happen? Well, if you think about what we talked about last class again, right? You have to have both ingredients in order to have circular motion. If you don't have enough velocity and you have too much centripetal force, what are you going to do? You're going to go towards the center, right? So there could be a case in which I have too much force going towards the center, and that would mean that I fall off here at the top, right? What's the minimum speed I can go at and make it around? Well, what that's really saying, let's draw this one more time. So what's that's really saying, right, is as I get slower and slower and slower, I need less and less centripetal force. Which force can change? Well, gravity can't, because the gravity is the gravity, right? The object has whatever weight it has. As it slows down, this normal force is going to get smaller and smaller and smaller until it can't get any smaller, because the normal force becomes zero. So that the minimum speed that I can make it to go around to still stay in contact with the track, the minimum speed I can go is when my centripetal force is equal to my force of gravity. So to find, again, the minimum speed the car could have at the top of the loop, I have to say that the centripetal force is only provided by the force of gravity and nothing else. I should write it. It should be consistent with how I'm writing it. I guess what I should say is that centripetal force is equal to MAC, and the centripetal force is equal to gravity. So we have mg equals mv squared over r. Does that make sense? Because again, if I'm going any slower than this, I've got too much force going towards the center. And what's the result? The result is I'm going to go towards the center. I'm going to fall off. Now, algebraically, we have this handy thing happen here where we've got a mass on both sides so they can cancel out. And then you can go ahead and solve that equation. That's what I got. Any questions? Another thing I want to make sure to point out, you'll notice here, my masses could cancel because every term had a mass. Up here, I can't cancel out my masses because that term doesn't have a mass. So just be careful. Don't cancel out masses when there isn't a mass in every term. You can only cancel a mass if it's in every term. All right. Here's what I'd like you to do, because you've got 20 minutes of class left. This is what I'd like you to do. I'd like you to go to today's folder and click on the day 37 assignment. And there are 2 problems here. I'd like you to work on these 2 problems. I'd like you to stay in the Zoom. I can't remember if we did that in this class or not, but I decided that that worked out better. So we'll just stay in the Zoom because then you can ask questions as they come up. But I'd like you to try these 2 problems here. And then once you finish those, you can upload them and you can be done at that point. But I want to give you some time here to do these 2 problems and then take a picture of it when you're done. I will be here to answer any questions you got. All right? So go ahead and get to work on that and then let me know what I can do to help.